While tests around means, proportions, and regression are some of the most common hypothesis tests done in statistics, there are many other interesting hypothesis tests that are worth looking at. One is a hypothesis test for a standard deviation. But before we can talk about testing the standard deviation, we need to talk about another distribution called the chi-squared distribution. The chi-squared distribution has several characteristics that are kind of unique from some of the other ones that we've seen thus far. The first characteristic is that this graph is non-symmetrical. In fact, more specifically, it is skewed right. Also, similar to the t-distribution, it has a certain number of degrees of freedom, but the degrees of freedom will significantly give a different shape based on the degrees of freedom. Another thing that's unique about the chi-squared that's different from the t and the z is that the test statistic, which is represented by the Greek letter chi and a little squared symbol on it, chi-squared is always positive. So when we graph the chi-squared distribution, it's always going to be just in the top right quadrant, the first quadrant. And then based on the degrees of freedom, the shape is really significantly different. This blue line might represent having degrees of freedom equal to 1. Maybe I'd have a graph like this green line that would represent having degrees of freedom equal to 4. Or maybe I'd have another graph, and that gray line might represent having degrees of freedom 9. So the shape is going to be dramatically different based on the degrees of freedom. As we sketch it, we usually do a sketch similar to the green line, just a hump and then leveling off skewed right. But it is significantly different based on that degrees of freedom. And so if we want to find some areas under this curve, as you might expect, we would use Excel to find the areas. And Excel has a different command for the left tail and the right tail. For the left tail, we're going to use equals CHISQ for chi-squared dot dist, open a parentheses. We'll do the x value that we're interested in, the numbers of degrees of freedom, and then we always have to end with true. If we wanted some area in the right tail, there is a right tail command, which is equals chi-squared dot dist. And we just add a dot RT for right tail, and then just x and degrees of freedom, and we don't need the true for this one. So, for example, if I want the area left of chi-squared equals 11 with 15 degrees of freedom, graphically what that means is there's going to be some chi-squared. We want the area left of x equals 11 in that left tail. So we can say equals chi-squared dot dist, open a parentheses, the value we care about of 11, the 15 degrees of freedom, and true. And when I do that, I'll end up with an area of 0.2474. Let's do an example where we're in the right tail. Let's find the area right of chi-squared equals 17 with 11 degrees of freedom. Graphically, then, what we're looking at is some type of chi-squared, but this time we're going to go from the value 17 and off to the right. To get the right tail, we'll say equals chi-sq dot dist. And then we'll do a dot RT to tell it we want the right tail from 17 with 11 degrees of freedom. And when I do that, I get an area of 0.1079. So that's the chi-squared distribution. This is the distribution we're going to have to use when we test the variance or the standard deviation of a population.